MOSFET can be modeled as an ideal voltage controlled current source as shown below. The control source is defined by I2 is equals to 2.5 V1 milliamps. So, as per the data, the I2 depends upon the value of V1. So, for the output pulse sequence, that is V2 is given as follows, that is 10, 0, 10, 10, 0 O's. Means this is the sequence which we are getting for V2. So, here V2 is decided by the I2, that is we can write V2 is nothing but 10 minus 2k into I2. So if we substitute 2.5, 10 minus 5V1 is nothing but a V2. Whenever V2 is equals to 10, if V2 is equals to 10, V1 is equals to 0. V2 is equals to 0 means V1 is equals to 2. So the sequence which we are getting here is 0, 2, 0, 2, that is option A is correct. Here the find the RMS value of the given waveform. This is y of t. So first of all write the equation for y of t, that is 10 plus 10 by t into t. This is the equation for the signal y of t. So first of all we have to find out the mean square value. RMS is nothing but the square root of the mean square value, that is 1 by t 0 to t y square dt, that is 1 by t 0 to t 10 plus 10t by t whole square dt. So 1 by t 0 to t 100 plus 200 t by t plus 100 t square dt. So 1 by t integrate 100, we will get it as 100t plus 200t by t square by 2 plus 100t square, that is t cube by 3. We have to substitute 0 to t. We will get 1 by t as 100t plus 200t plus 100t by 3. So we will get this as 1 by t 200t plus 100t by 3, that is nothing but 700 by 3. We will get mean square value. So RMS value is nothing but under root 700 by 3, which is nothing but 15.2, that is option B is correct. A MOS capacitor in which semiconductor is silicon doped to Na is equals to 10 power 16 centimeter power minus cube at T equals to 300 Kelvin, and intrinsic carrier concentration is 1.5 into 10 power 10 centimeter power minus cube. Calculate the maximum space charge width given a particular semiconductor doping concentration. See here the built-in potential, that is pi fp is equals to Vt natural logarithm of Na by Ni. If we substitute the respective values as follows, that is we will get this as 0.347 volts. Maximum space charge width, that is XD, is denoted as 2 epsilon s. Semiconductor is silicon, so we have to indicate 2 epsilon s pi s, that is surface potential, divided by QNA under root. Here surface potential pi s is nothing but 2 into pi fp. So if we substitute the given, because you see we got pi fp, means we can decide pi s. Epsilon s is nothing but epsilon naught into epsilon silicon relative permittivity, that is relative permittivity of silicon is nothing but 12. So Q is the charge of an electron. So if we substitute the given values, we will get the space charge width as 0.30 micrometers, which is option C is correct. Find the gain of the circuit shown below. So if I am indicating this as VA, from the virtually short circuit concept, this node having the potential VI. So if we apply the KCL at VA as well as node VI, we will get as VA minus VI by 1, VA by 2, VA minus V0 by 2 is equals to 0. That is equation 1. If we apply the KCL at node VI, that is VI by 1, VI minus V0 by 1 is equals to 0. From this equation we will get VA as 2VI. This is equation 2. So solve the equation 1. VA minus VI, VA plus VA minus V0 is equals to 0. So V0 is equals to 4VA minus 2VI. VA is nothing but 2VI from the equation 2. So this is V0 is equals to 8VI minus 2VI, which is equals to 6VI. Hence gain is V0 by VI, that is A is equals to 6. That is option B is correct. The inverse jet transform of a given expression, that is Az into Z plus A divided by Z minus A whole cube. Here f of n, suppose an u of n, whose jet transform is f of z is z by z minus a. If we find d square f of z, we will get this as 2a z minus a whole cube n square f of n is equals to n square an u of n, which is equals, if we apply the z transform to this equation, we will get z d by dz f of z plus z square dz square f of z. Z d by dz f of z is equals to minus az z minus a whole square. So by substituting these two values into this equation, we will get n square a power n u of n is equals to az z plus a divided by z minus a whole cube. Hence option C is correct.